Hi everyone. For today's class, we'll talk about actually this is part two, no, of statistical computations because we did the part one of this last time, where we talk about the descriptive statistics, no, because I already mentioned to you that when you talk about statistics, we can talk of two branches, no, the descriptive statistics and the inferential statistics, no. What we focused last time is more on the descriptive statistics, meaning we describe our data using measures, no? Using measures of, actually we tackled about three measures, no? Measures of central tendency, measures of dispersion, or we also call it variation or spread, no? And the last one is the measures of relative position. And we discussed three measures for each, but it doesn't mean that those are the only measures, no? For each, no, it doesn't follow. Those are the main measures, no. For example, in the measures of central tendency, we discussed three, no, mean, median, mode, and among the three, the most commonly used is the mean, but it doesn't mean it's the most appropriate for. It depends on the study, because possible that the median or the mode is the more or most appropriate measure of central tendency for another study. If we want to describe our data in terms of its center, no? In terms of its center. Now, the second measure, the measures of dispersion, variation, or variation, dispersion, or the spread, no? As we also call it, spread of your data. We also discussed three there, no? The range, standard deviation, and the variance. And the most commonly used is the standard deviation. But again, for some studies, range or the standard variance can be more or most appropriate, no? But the most commonly used is standard deviation. Where if we want to, if you want to describe our data in terms of the spread or how disperse your data from the mean, from the mean. That's why in the formula of the standard deviation or the variance, the mean is in the formula, right? It's in the formula. And then the last measure, which is the measures of relative position, again, we also tackled three measures there: the z-score, the percentile, and the quartile. No. Okay, so their class now, we want to describe our data in terms of the position of your particular data value, no? Position. Okay, the relative position. Then we use that, no? Actually, we'll use implicitly or explicitly these measures, no, in the second part, no. Actually, this one is the focus is more on statistical distributions. Now we'll talk about distributions, no, distributions of our data, whether that data is population or sample, no. So we'll talk of the distribution. So when we say distribution, no? So it's not. It's kind of related to variability, no, but it's still different, no. Here, class, as in all data are considered, no. All data values are considered. So when we talk of distribution, we can talk of population distribution or sample distribution, or discrete distribution or continuous distribution. Actually, we'll tackle more on this on the on the 12th week, before the 13th week. It's like the second lesson from the last lesson, no? Which has to do with this discrete and continuous probability distributions or population distributions, no? However, after today's lesson, we'll tackle just one continuous, one example of a continuous probability distribution or population distribution. Okay, the others, we'll tackle them, no? We'll skip some. I think I will skip. We'll study first another two lessons, and then after that, we'll go back to this lesson. Okay, it's just like the data science. When we discuss science, second lesson, and then when we studied other lessons, and then we go back to the study of data science again. And we'll do similar thing for this one. I don't know why is there such a break when it comes to the discussion, no? Interruption when it comes to the discussion of a topic, no? So anyway, so that's what you will expect for today's lesson, no? So some concepts, if not implicitly or explicitly, discussed last lesson, the part one, will still be mentioned here, no? either implicitly or explicitly. Okay, especially that part on the z-score, no, z-score, no. Remember I told you about that, the z-score, that we will discuss more about the z-score in our lesson, and this is the time, no. And also on the, yeah, on the 12th week, no, it still be tackled, no, that z-score related to this distribution that we will discuss now, no. Okay, so what are the major topics that we will tackle here, no? So what are the major topics? So also, just like in the last lesson, we have three major topics, no? Frequency distribution, a normal distribution, then standard normal distribution. So this is the normal distribution that I'm talking about, no? Which is an example of continuous probability distribution, or the continuous continuous population distribution. Okay, as distinct from the discrete distribution, because there's what you call discrete, no? But we'll tackle more about that next time, no? On the 12th week, no? Yeah. So I think we can discuss now this one, the frequency distribution, which is the first part. Okay, let's go to the next slide to discuss frequency distribution. Okay, so we have these three definitions, and then I'll give example for each class. No? So what's the group frequency distribution? Where large data sets are displayed. No? Large data sets are displayed. And then histogram, a graph used to indicate intervals in the frequency distribution. And then there's a relative frequency distribution. List the percent of data in each class interval. So these two classes are tables. No? I'll show you a table for this and also this one. This one is a graph. A graph, meaning to say, if you have your data, remember, in part 1, we talk about raw data, ungrouped data, and then group data. Usually, the raw data is the ungrouped data. So once you put it in a table, which we call the frequency distribution table or the relative frequency distribution table, then you have a group data. That's why you notice here grouped. It's one way to organize your data. No? One way to organize your data is to put it in a table or in a graph. In this case, we use histogram. But of course, there are other graphs, no? Where we can present or organize your data. No? Not only histogram. So there are other graphs such as pie, bar graph, line graph, not to organize or present your data. Okay. And aside from graphical, these two tables, no? The tabular form of presenting or organizing your data, tabular form. And we have two examples here, no? The frequency, the group frequency distribution table, and the relative frequency distribution table. There's another one of how presenting your data or organizing your data, the textual. When you say textual form, using paragraphs, no? Using paragraphs. Okay, but the problem with the textual form, you cannot mention, no? You can only mention the summary there, no? Not so much details. No? Unlike the histogram, you can see other details, no? Or more of this, the table, these two tables, no? You can see some details, no? Unlike in a textual form of presenting your data, usually what you mention there is a summary of your data. Not so much on the details. But of course, there's also disadvantage. No? I'll mention to you, this, especially this one under the table, some disadvantages as well. Okay, class, let's discuss the examples. No? Examples for each. No? So this one is the frequency distribution table, where you see that intervals and the corresponding frequency. That's why it's called frequency table. No? So for example, class, this 0 to 5, for example, in your raw data, remember, before you can come up with this table, you should have your raw data or ungrouped data. So example, let us say in this 0 to 5, you have the download, include the 0 download time. Is that possible? 0? Because possible also, class, you have 0 to 5, but you don't have 0 in your data. No? You don't have 0 in your data. So let's say 0, and then you have 1, then another 1 in your data, and then you also have 2, which can be found in this interval because 0 to 5. And then you have 3. So how many do you have now? 1, 2, 3, 4, 5. And probably you have here 4. So all in all 6. No? That's why you have 6 here. So that's the meaning here. No? That's the meaning here of class. The number of subscribers, no, and the download time. So you have this raw data, which you listed them first, probably not arranged. That's why unorganized, no, ungroup data or raw data, no. 1, 2, 3, 4, 5, 6. How about if you have 5? You include the 5. Where will you put it? In this interval or this interval? Okay, there's an understanding that when you have this, it means under 5, 0 to 5. Under 10, less than 10, meaning, no? Under 15, less than 15, and so on and so forth. Even if you don't indicate it, that's the understanding. So meaning to say, the 5 you have to put here, 5 to 10. Because under 5, so this one is not included in this interval. It has to be counted here, meaning this 5 here is one of the 17. Okay, so what's the disadvantage, as I mentioned to you, no? If you don't know the raw data or the ungrouped data, you don't know, you only have this. The disadvantage is you don't know the details, no? What are the particular 6 data values you refer? Well, you know it's between 0 to 5, but what are the particular? So from the raw data, you'll be able, probably you'll be able to see something like this, no, as in exact. No? So that's the advantage of having raw data or ungrouped data. But the problem with the ungrouped data, especially if it's a big data or large data, it's hard to, you cannot analyze them, right? So you really have to organize them in a way that you can analyze them, no? So that's the problem. Okay, actually, as long as you have the copy of the raw data or the group ungrouped data, no problem of no, organizing your data this way, no? Because once you have the you have your raw data or the ungrouped data or unorganized data, even if you put 6 here, you have a file for this. So you know the meaning of 6. What are these 6? Probably in your raw data file or in your ungrouped data file, you can see this, no? Possible, no? Except 5. Because the 5 is included here, no? Only an example, no? Okay, so question is how to construct, no? How do you construct frequency distribution table? Okay, let's recall class now. Let's recall how to construct frequency distribution table. So again, as I mentioned, we'll use some of the concepts we learned in part 1, if not implicitly, explicitly. This range, no, the measure of dispersion, the range, no. So example only, the example is, for example, the minimum value is 0, the maximum is 60. So get the range. Now the range there is 60. And then that range, you divide it by the number of your desired classes, no? Desired number of class intervals. In this case, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 60 divided by 12 is 5. That will be your class width, no? Meaning class size. For example, how do you get that? Subtract this, no? 5 minus 0, 5. 10 minus 5, 5. So that's the meaning. Because you must have a uniform size for each interval or a uniform class width, no? Once you have that, and you already established your minimum and maximum, the minimum and maximum class for the interval do not have to be in the data, no? In your raw data. Okay, this is an example where 0 and 60, for example, is in your raw data. But it's possible that the 0 here is not in your raw data, or the 60 here is not in your raw data. That's possible. Because what's important, class, is that all the raw data are present in one of this, only in one, no? Of the, you cannot repeat, no? You can't have like 4. That's why, for example, the 5 you include here, you also include here. That's why we make a distinction, no? When we say 0 to 5, we mean less than 5, under 5. When we say 5 to 10, it means less than 10, under 10. That's why there will be no repetition. You know that if it's 5, you have to put here. You have to count here, not here, even though you see the 5 here. It's understood. But there are some frequency distribution tables wherein you have to write that. No? There are other references. They mention that the under 5 or less than 5, no? Not simply as 0 to 5, 5 to 10, because there might be a misunderstanding of that you put the 5 here, you also put the 5 here. Okay, possible a misunderstanding. No? That's why you have to put the under, no, or less than. Since I already told you, so we don't have that misunderstanding already, no. So we know the 5 is counted here, not here. Okay, so so as I mentioned, these two, Not necessarily to be in the ano, no. Even the endpoints, no. The 10 here, the 15 here, not necessarily to be in this data, no. Not necessarily. What's important, all the data, you can find it in one, exactly one of the intervals. It cannot be at least one, in one of the intervals. So if you cannot find data with, don't include this, of course. You don't include 0 to 5, no? If, for example, you don't have data between 0 to 5, don't include that. So you start here, 5 to 10. So you don't really have to start always from 0. No, there's no need. Because possible, your minimum is not here, no? Probably your minimum is 6, not 5. So you have to include this, 5 to 10. But no need to include this if you don't have data within this interval, no? So it's not always 0 to 5. It's not always like 0, you start from 0. No, you can even start here, no? It depends on your minimum. If your minimum is 11 or 12, then you don't need this 2. You only need this 10 to 15 up to 55 to 60. If your highest is here, no? If you have values within here, for example, your highest is 55, you still have to include this, even though there's only one. For example, only one, no? You have to follow the computation. Your computation, based on your computation, the interval size is 5. So you have to include that interval, 55 to 60, even though you only have one, which is 55. Okay? You have to include that. So what's important, as I mentioned, all the data values in your raw data or group data should be found in exactly one of the intervals, and no repetition. Okay, so usually class, it's 5 to what do you call this? 5 to 10, no? I'm sorry, 5 to 15 class intervals. But I want you to explore on that one, on that aspect, no? On how to find the class intervals. No, I think this is just a review on your part. I think you learned this already. So how do you determine the number of class intervals when you construct? Usually the ideal is 5 to 15. So we have here 12, no? Okay, so now you know how to get the class size. Again, let me repeat. To get the class size or the class width, your range, you know how to get your range, no? You have your raw data, and then you get the minimum and maximum in your raw data, and then get the range, the difference between the two, divide that by the number of desired class intervals. No, here we want 12. That's why divided by 12. 60, for example only 60 is the range. 60 divided by 12, 5. Okay, so I want 12 class intervals with the size of 5. And then I want to start from 0 and then end with 16. No? So you should be the one to, based on that computation. No? Based on that computation. Okay? I think that's clear. So this is an example of a frequency distribution table. So how about the next one? Histogram. A graph used to indicate intervals in a frequency distribution. So meaning you just graph this in another form. Present this data in another form. Instead of table, use a graph. Okay, but you might think this is you might think of this as a bar, no? There's similarity, but they're different also, no? What's the similarity? Both of them have rectangles, no? This one has rectangles. Remember the bar graph? You have rectangle, either vertical or horizontal. Here, class, we also have rectangles or bars, but the difference is that because in a bar graph or bar chart, these rectangles, between two rectangles, you have spaces. Whereas in histogram, we don't have spaces. You have to draw them side by side, no? With no space. Example. Let's have an example. Let me draw, but of course not accurate, just to give you an idea on how to do it. So just similar to the bar graph, you have the Y and the X, no? The X. And then you label, no? For example, the x-axis, your label is number of subscribers. I won't write it anymore, no, because it will take a longer time. Number of subscribers here, you have to write number of subscribers. And then the Y, download time. And then you have to put the numbers, no? Here, class, what will be the numbers here? This one, the class endpoints. When I say class endpoints, I'm talking about this class interval. It has a class endpoint 0 and 5. This class interval has the class endpoints 5 and 10. Or another, you can also call them limit, no? Lower limit, upper limit. Okay, so you have to indicate here, no? So that's another difference, no? When you compare it to bar, no? In bar, we don't really have to put this, no? But here, class, you have to, like a number line, no? Like a number line. So we have here like 5, no? Then this one is 0, 0, and then 10. So only the class endpoints, no? 5, 10, 15, 20, no? 15, and so on and so forth until you reach 60, no? So you finish until 60. So in effect, class, you will have how many rectangles? 12, because you have 12 class intervals, no? So I'm just giving you how to construct your histogram, no? For this one, class, you may decide, no? This one, the interval is 5, no? This one can be, it depends, no? It depends here, class, because this is the number of subscribers. So we can use 10, 10, 20, 30, 40. Because I have 10 here, no? So here, 190, no? So until I reach 200. Or probably because we have 192. That's why we have to include 200, no? 190, then 200. Because the highest here is 192. But the lowest is, what's the lowest? 6, no? So I think 10 is okay. So we can have, as long as equal, no? But of course, mine is not accurate. But it has to be accurate, class, huh? So you have, for example, 10, 20, until you reach 200, no? 200. It's up to you. You may use 50, but I think it's hard to not to graph it, no, if it's like that. So I think by tens is fine. But you can do that if you can graph it well. Okay, and so on and so forth. But if you look at my graph, it's not accurate. But I believe you got my idea, no? Okay. This one up to what? Up to 60, right? Because of 0 to 60. This one is 10 to 200 because of the 192. 10 to 200, no, because of the 192. Okay, let's start with the 0 to 5. 0 to 5, 6. So less than 10. So probably here. So this is 5. So probably here. No, again, it's not accurate. And it has to be straight, class, high, straight. Excuse me. Because when I write it, it's sliding, no? That's why I have problem writing on the screen. 5 to 10 is 17. So less than 20, no? Less than 20. So probably this is 15. So just above it, no? So, but you have to continue this straight, no? Straight. It has to be straight. And then like that. Okay. You notice there's no space between the two. So that's the difference when you compare this to bar chart, no? Or bar graph. Okay, so 10 to 15 is 43. So if there's 30 here, probably this is 40. Okay, let's say this is 40. And then you have here 50, no? Because that's 43, 50. So the 43 probably here. So below 45, right? So 10 to 15, 43. So below 40, 45. So if this 40, probably 45 is here. Since it's 43, so below 45. So again, it's not accurate. So what I just want to point out is, you notice you have to draw the rectangle beside each other, no? No space. See, no space. So that's the difference when you talk of histogram. Okay? So we'll have how many? 12 rectangles and drawn next to each other, no? As in no space between the two rectangles. Whereas in a bar chart, bar graph, you have spaces, no? You leave spaces between the two. And then you don't label it like this, no? That's why you have to label it like this, because it's like continuous, no? As in no space, That's why you have to label it this way. And put label here also, you put download time, the proper way, no? Of drawing the graph, any graph, no? Whether it's, even though it's not histogram, no? The number of subscribers for this. It's just that I did not write it anymore because of it take longer time. But as long as you understand what I mean, no need to write it here. Okay, class. So I think that's clear. So here, class, now we have all the datas are considered, no? But of course, compared to raw data and group data, yeah, it's just unorganized. But we can see all the data. That's the only advantage, no, for the raw. But there's no use, class, no? Especially if it's big data and it's unorganized. Try to imagine, no? Looking at numbers, 1,000 numbers, and no organization. Okay, so how can you analyze them? That's why there's a need for putting it in a graph or in a table, no? And when you put it in a table, or in a graph, we can apply some some analysis, no, or some tools to analyze the table or to analyze your graph, no, not just by looking at it, no, not just by looking at the at the table or the graph. Okay, in fact, for the next table, we come up with that because of this table, no, and that table is called the relative frequency. As mentioned here, the relative frequency distribution leads the percent of data in each class interval. Now, this percent class can be in decimal, no? Decimal. But of course, if you put it in percent, when you add all of them, it's 100%. But if you use decimal, when you add all of this, it will be 1. Okay? So I think you know how to get it because of the word percent, right? So to get the relative frequency distribution table, which you base here, get the total. For example, this population, if this is a sample, we denote it as sample size, denote it as small n. If it's a population, we denote it as capital N. So let us say this is a population. No? So the capital N, when you add all of this, is equal to 1,000. 1,000. Okay, so never mind my handwriting because it's sliding. It's sliding. Okay, so to get the percent, divide this by 1,000. No, 1,000. So if you divide that with 1,000, you get a decimal, which is, remember the rule, if you have 3 zeros, the decimal point is here. So move this 3 to the left. 1, 2, 3. If you want, you do it manually or use calculator, no? But that's the technique. That's why the answer is 0.006. 0.0 in decimal. You do the same thing for all, no? You divide by 1,000, you get a decimal. When you add all of those, it's equal to 1. But if you put this in percent, you have to move this 2 places to the right. That's why in the relative frequency, we use percent. That's why it's 0.6%. 0.6. Because from the decimal, 0.006, you change it to percent. And that's the rule. Now move the decimal point 2 places to the right. And we get 0.6. But again, if you add all of this decimal 1, whereas in this one, when you add all of this, it's equal to 100%. Okay, so again, for a relative frequency distribution table, it's all right to have percent or decimal. Okay, usually actually class usually decimal, decimal, because right later, no, we will associate this to probability, no, and we talk of probability usually it's in decimal form, probability. But again, probability can also be in in percent, no problem. Okay, but later on we'll discuss this certain table wherein the numbers there are decimal, no, not percent, no. Okay, anyway, later on the third part. We're still on the first part, no? Still on the first part. Okay, to proceed, I think we have some problems to solve. Yes, using the relative, no? The relative. Not the frequency distribution table, but the relative, meaning but this relative we got it from the from this frequency distribution table, no? Okay. So yeah. So let's proceed. So this is the problems now. Percent of subscribers who required at least 25 seconds to download the file. At least. So meaning it's like greater than or equal. Okay. Probability that the subscriber chosen at random will require at least 5 seconds but less than. So meaning there's like, so if our data value is x sub I, so let's say x sub I, so we want x sub I to be greater than or equal to 25, something like that, no? So we want to count all those data values from our raw data. Now, for example, we have our raw data. We want to count all those data values which are greater than or equal to 25. Okay, in percent. Okay, but of course in raw data, as in raw, that's what you will get, no? That's what you will get. Meaning the one you got in the frequency distribution table, no? Where is that? No, it's not also. Yes, because this one are like coming from the raw data, right? Okay, but what we want here is not that. Instead, it's the percent, no? Okay, this one probability. Now it's mentioned probability, no? Versus percent. Okay, probability that a subscriber chosen at random will require at least 5 seconds. So if x sub I is your we're talking about that. So we're getting all this, no, and then greater than or equal to 5, but less than but less than 25. So what probability or what percent of your data? Okay, just the percent, no? If you want to know the, as in exactly how many, you base it on 1,000 because we have 1,000 data values, right? I'm sorry, yeah, we have 1,000. So if you want to know how many from 1,000, you multiply that percent to this one to know from the 1,000 data values, no? Okay, but here it's just a percent. So what do you do? Let's discuss one by one. So the first problem, percent of subscribers who required at least 25 seconds to download the file. So take the sum of the percent of subscribers from this interval to 55, 60, because we want x sub I to be greater than or equal to 25. So it makes sense, right? It makes sense because if you look at the table, so this one, right? So from here, so count, because this one is at least 25 seconds, no? So in other words, you add all of this, no? And you will get the percent. Okay, so 19.2 plus 19 is 38.2, right? 38.2 plus 14 is what? 38 is what? 52, 53.1, right? 53.1 plus 9 is 62.1. 62.1, you will get here 66.6. 66.6, you will get what? 68.1 plus 1, 69.1. So indeed, the answer is correct, right? We get 69.1%. That is percent, no? Now, if you want to get the exact number of subscribers, the exact number, not just the percent, multiply this by 1,000. Okay? That's why you put it in percent, because this number of subscribers can change, no? You want to generalize it, no? So in effect, you will get, because in decimal, this is 691.691. So times 1,000, you will get 691. 691. But that's not the question, right? The question is just percent. So we want to go beyond the question. For example, there's a question, how many subscribers? How many subscribers required at least 25 seconds to download the file? So you base it on the 1,000, which is the population size. So 691 subscribers. Okay. But if the question is only percent, so this is enough, 69.1%. Okay. Just to relate it to the number, to the population size. Okay. How about the next one? Probability that a subscriber chosen at random will require at least 5, but less than 25 seconds to download the file. So this one is talking of like subscriber only, a subscriber. So this 1% of subscribers, that's why we can relate it to the number of subscribers. This one class has to do with the probability that a subscriber chosen at random will require at least 5 seconds, but less than 25 seconds to download the file. Now we'll use the same table, class, no? Just like the table that we use in A, we'll use the same table. It's just that the focus here is the probability, and we're talking of 1 subscriber. Whereas here, class, we're talking of not 1 subscriber, but among the 1,000 subscribers, how many subscribers who required at least 25 seconds to download, no? So you notice the difference in the question, but using the same table, no? We will use the same table. In fact, the same method, no? The same method of getting the answer, no? The same method. Okay, but different different understanding. Okay, different perspective. This one is probability. So that's why we introduce this word probability, no? Not just percent, not just the decimal, no? Because in fact, that's why we mentioned distribution. We also call population distribution probability distribution. Okay, we'll tackle more of this on the 12th week, no? This probability distribution. But for now, we're initially mentioning to you that it's connected to probability, no? Not just the number, no, but probability. So it's just not plainly percent or or what do you call this, or decimal number that we're talking about here, but it's associated to probability. And this is an example of a question, wherein we'll use the same table. So that in that table, take the sum of all the percent of subscribers from the interval 5 to 10 to 15 to 20 and divide by 100 to obtain 0.152. As you notice, I mentioned if the probability, usually we want decimal. If this is percent, this is 15.2. In fact, when you add all of those, you will get 15.2 because in the table, you have percent, not decimal. Since we're talking probability, we want to change the percent to decimal. Okay, let's go to the table. So what is that? 5, 10, and 15, 20, no? We consider those intervals and we add 5, 10. So this, no? This 2. This 3. You add this 3. Because you want what? Greater than 5 but less than 25, no? So this 3. So what's 1.7 plus 4.36 plus 9.2, 15.2. So indeed, we get the answer, no? 15.2. Where is that? 15.2%. But again, since we're talking of not the 15.2% of the 1,000, instead, the probability that is a subscriber. Okay, and that probability is 0.152. So if you are a subscriber, the probability that you will chosen at random will require at least 5 seconds, but less than 25 seconds to download the file. The probability is 0.152. Okay, so less than 1. Okay, so I believe you understand that. Okay, so now I think the next one is to do with the next part already, if I'm not mistaken. No? Yes, the normal distribution. Okay, or the one where we associate a probability, na? Where we associate probability, na? That's why this is also called a probability distribution, a type of probability distribution, which is a normal distribution or a type of continuous probability distribution or population distribution, normal distribution. So as I mentioned, there are other types, no, of probability distribution or population distribution, or in particular, continuous probability distribution, okay, which we'll discuss on the 12th week. And aside from the continuous, we have discrete, no? So we also have types of discrete probability distribution or discrete population distribution. So this is just a glimpse, no, of that topic, no? The normal distribution. Okay, so what's this normal distribution? Okay, from this website, no, I got this from this website. Many things closely follow a normal distribution. So when you talk of heights of the people, size of things produced by machines, errors in measurements, blood pressure, marks on a test, it follows a normal distribution, especially if your data is big. If you're dealing with a big data, if you graph them, you will come up with this graph, this kind of graph. We say data is normally distributed if we have this kind of graph, no? Where the mean, median, and mode are equal, no? And this property, symmetry about the center. And 50% of the values less than the mean, the other 50% greater than the mean. So if the mean is 50, for example, it's 50, so expect that all the data values, 50% of your data values are greater than 50. The other 50% less than 50. Okay, so again, that will only happen, class, if you have big data. That's why, you know, remember we discussed about important, no? That it's based on the big data. That it's okay to talk about simple model, or more useful, no, to talk about simple model based on big data than a complex model based on small data. And one of the reasons is because if you have large data here, we can have this graph, and once we have this graph, it has a lot of applications, a lot of uses, no? Okay, a lot of uses. Okay, so probably you'll be able to realize that one of the uses, no, or some, as after we finish the lesson, and more when we discuss again this topic on the 12th week. So we have to discuss other topics like a break, no? Other topics. That's like when we talk about data science, no? We discuss data science, and then for some weeks we discuss other topics not related to data science, and then we talk about data science again. So we'll do the same thing for this topic, no? Okay, so there's like a break. Probably during that time, that's the time that you explore more about this topic, so that when we talk about other topics related to this, somehow you have a knowledge already, no? So easy, you can appreciate it more, no? So anyway, let's talk more about this. This normal distribution. So as mentioned in your module, obviously it forms a bell-shaped curve, no? If you look at it, yes, it bell-shaped curve, and that is symmetric about a vertical line through the mean of the data, as already mentioned here, no, in this website also, no? Symmetry about the center. So about the mean. Okay, where the mean equals the median equals the mode. No? So now, in your module, this is mentioned, no? Empirical rule for a normal distribution. But what's the meaning of this percent? No? We'll tackle more about this later, no? The details. So 68% of the data lie within one standard deviation of the mean. So what's the meaning of that? It's 95% of the data lie within two standard deviations of the mean. 99.7% of the data lie with three standard deviations of the mean. So what's the meaning of all these percents? So, okay, let's look at this website. From this website, no, I got this. Okay, so if you'll notice, we have here 68.2, but it's all right to say 68 only, no, if you round it off. And here 95%, but in this website, 95.4, no? Again, when you round it off, 95, so no problem. But the 99.7, no problem, not the same. No, it's the same thing. Okay, so how do you analyze this? So this is a normal because of those properties that we already discussed. So this is the population mean because mu, and then standard deviation. But let me just add something here, class, because I have a problem with the one standard deviation here. Better to put instead of one standard deviation, put the mu. It has to be a mu plus. Okay, the mean plus the one standard deviation. Also this one, mu plus. So there's a mu. Also this one, mu plus. Okay, so we'll concretize this later. Now we will concretize. Now this one, class, also the same, no? Mu minus. Also this one, mu minus, and then mu minus 3 standard deviation. Okay, so meaning to say, class, if you have x sub I, so x sub I are your data values, right? Data values. Meaning, if your x sub I are inside the green portion, here or there, as long as inside the green, then we can say that these data values where you are located in the green shaded area have values can be greater than this mu minus 1 standard deviation, but less than mu. This is not 16. This is standard sigma. 1 plus, remember we denote standard deviation as sigma, population standard deviation, as we talk about this last the last lesson. And then this one, mu plus 1 standard deviation. Okay? And how many x sub I with this property? 68%. 68%. So if your population size is 1,000, for example, 1,000 as this example only, or it can be 100, or let's say 100. Okay, you're talking of 100 data values, or just make it 1,000 to be consistent. So just get the 68%. So what's the 68% of 1,000? 680. So meaning to say 680 are here, located here in the green. 680 of your data out of the 1,000 are here, and their values are greater than this, but less than this. Okay, can be equal, no problem. You can, I'm sorry. You can make it equal. Okay, so that's the meaning here, class, of 68. So now I think you know what it will happen, no? What it will happen if we talk about 95%, no? So we're talking of the green and the yellow. So if your x sub I is greater than or equal to what? This one, the u. This one now 2 standard deviations. U minus 2 standard deviations, but less than equal to mu plus what? 2 standard deviations. Meaning you can find x sub I either in the green or in the yellow. And how many x sub I do you have with this property? You have 95%, no? So let's say 95, not 95.4. Then get the 95% of this. So you have 950. Now, if you want to stick to 995.4, then 954. 954 of your data values will have values between these two and located in yellow or in green. Okay, you got it now? You understand? We'll concretize this later, no? We will concretize. This is like general. Eh? I think you know now what will happen if you have ano, no, mu minus 3 theta and then mu plus 3 theta. It will be 99.7. So meaning 997 out of the 1,000 have values greater than mu minus 3 theta but less than mu plus 3 theta, or you can have equal, no? Less than or equal this but greater than or equal this but less than or equal this, no? Okay? So that's the use of the empirical. This empirical rule. Okay? Now, let's to understand this better, let's try to solve problems, particular problems using this empirical rule. Okay? So this is the problem given in your module. A survey of 1,000 US gas stations, so 1,000 again, found that the price charged for a gallon of regular gas could be closely approximated by a normal distribution. Okay, so now I think you can see the application. No? If it's a normal distribution, we can solve this problem. No? So approximated by a normal distribution with a mean of 3.10. So this is the mean, this is the mu. And the standard deviation of, so this is the sigma, 0.18. So how many of the stations, out of the 1,000, how many of the stations charge between this for a gallon of regular gas, or less than this for a gallon of regular gas, or more than this for a gallon of regular gas? So how do you get the answer? Okay, that's where we will use the property of normal distribution. So let me go back to that and concretize, no? Concretize this. Instead of using the mu and the, what's this? The sigma, let's put values mentioned in the problem. So let me erase this. But I will use eraser, no class, not the pen. So let me erase that one. And we will use values, no, specific values. But again, it's still 1,000, no? So let me not erase the 1,000 here. Okay, so let's just concretize. So what's the mu here again? The mu is, as mentioned, 3.10. So mu here is this one. So meaning this one is 3.10, no? This is 3.10. Okay, 3.10. But what is the sigma? I should have not erased the mu minus. Anyway, what is the sigma? 0.18, right? So the sigma is 0.18. Okay. So meaning class, this one is, remember, this one is what? Mu plus, no? Mu plus 1 sigma. So this one, because mu is 3.10 and sigma is 0.18, we can have a specific value, no, equal to something, right? What is this equal to? That's the question. How about this? Also this one, right? Because we can just substitute. We can get the value of this. Mu, no class? Mu plus 2 sigma. So we have a value for this one also. And also this one, right? Okay, you try to compute now. Okay, so similarly for this, mu minus, no? We can get a specific value as in number, real number. And also this, no? Based on the given, mu is 3.10, a sigma is 0.18. So now it's more concrete, right? Not general. So this is equal to something. And we relate this to the problem. So let's go back to the problem. Let's discuss the first one. The first one, letter A. So it's mentioned here, class, that this interval is 2 standard deviations below and above the mean. That's why it covers 95, no? So 95% of 1,000 is 950. So the answer to the problem is 950 stations. But question is how to get the 95%. Because as mentioned, 2 standard deviations. Remember, in the empirical rule, if you have 2 standard deviations, that represents 95% of your data. But again, how to get that? No? How do you know it's 2 standard deviations? Okay, it has to do with this. Okay, remember, what's the mean again? The mean is 3.10, right? And the sigma is 0.18. Now, try to compute this, class. Try to compute this. Mu plus ano? What is mu plus 1? 1 sigma. Okay? Or better, 2. Because it's mentioned here 2, right? 2. What is mu plus 2 sigma? Isn't it equal to, ano? Mu is 3.10. What is 2 times 0.18? 0.36, right? So what is 3.10 plus 0.36? 3 point what? 3.46, right? And you notice we have 3.46 here. 3.46. Okay, so that's why now we can write this as 3.46, no? Going back to the ano. So this mu plus 2 theta is equal to 3.46, no? 3.46. Okay, this mu plus. But how about the mu minus 2 sigma? What is that equal to? Now, just compute again. Compute. So what is mu minus 2 sigma? So again, 2 times 0.18 is 0.36. So 3.10 minus 0.36 is, if you will know that, it's 2.74. If you compute that, that's 2.74. And again, we have that here, no? And in the question, it's there. So that's why, going back to the graph, this one is equal to 2.74. So now, you notice the yellow and the green. The yellow and the green represents the 95% or the 95.4%. That's why, you know, the among the 1,000, the 95% of 1,000, which is 950, have values greater than 2.74 or greater than or equal to 2.74, but less than or equal to 3.46. So that answers the question, right? Between 2.74 and 3.46, how many stations charge? So that answers the question. 950. So that's how you use the empirical rule class, no, to answer problem like this. Okay, did you get? I believe you got it. No? Now let's proceed to the next one. Next problem. So this one less than 3.28. But what is 3.28? As mentioned here, the 3.28 is 1 standard deviation above the mean. Right? 1 standard, because again, what's the mean? The mean is 3.10, right? And then the standard deviation is 0.18. So when you say 3.28 is 1 standard deviation, this one, because of this, no? Mu plus 1 standard deviation, meaning above the mean, plus if it's below the mean, minus. So 1 standard deviation is equal to, I think you know already, right? 3.10 plus 0.18 is 3.28. So again, you notice 3.28 is the same thing here, no? It's just the same. Now, if going back to the graph, so we know already that mu plus 1 sigma is 3.28. So going back, so this one here is 3.28. 3.28. Okay? Okay, so 3.28. So I suggest class you must have a graph also, no? So that you can write them legibly, no? Unlike what I'm writing now, not so legible, because I have problem, no? It's sliding, It's sliding. But I believe you understand what I mean. So this one is 3.46, this one is 3.28. So how do we answer the problem using the empirical rule or using this this graph? So what we want is, what do we want? This problem, no? More than 3.46 for a gallon of regular gas. So meaning we want to know how many of the stations, no? So we want to know, if we go back to this, so this is 3.28. So meaning we want to know this, no? This part, all of this, including the red and the yellow. Okay, the yellow and the red here. We want to know, first we want to know what percent is this. So that once you get the percent, multiply that by 1,000. That's the answer. Okay. But how do you get that percent? Okay, let me go back. Isn't it? Less than. I'm sorry, class. It's less than, I'm sorry. I'm talking about the 3.46. So if it's less than, it's the opposite. We want to know all of this. Okay, so let me use another color. The other color, probably blue. Yeah, blue. So we want to know all of this. No? Okay, again, it's slides only within the graph, class, within the graph. All of this. So all of this. The green, both the green here and the yellow here. And the red here. So not including this, no? Not including. So we want to know the percent here. But if you will look at it, because we have the percent already, that's easy to find, right? That's easy to find. Because we know half of this is 50. So this is already 50. And we know this green is 34 without considering the 0.1. So that means we have what? 50 plus 34, 84%. So the answer is 84. So 84% of 1,000 is 840. That's why we got 840 here. Okay, the answer is 840. Simple as that. No, but this one is divided into two. First, consider the other half. That's why 340. Then the other half, 500. Then add the 2. But I can just use the 84%, no, instead of just using the 34% because it's the same. It's the same answer, no. In fact, that's what happened here. It's just that this one is 50%, no. 50% plus 34% is 84%. But you can just answer the problem directly if you use 84%. 84% of 1,000 is 840. Okay. Now, if I want to add another problem, for example, I want to answer the problem wherein more than 3.28. So that's the one I consider, no? The other shade, the red. So 100% minus 84%, 16%, no? So meaning that red here. So that's 16 because if this is 84, the whole thing is 100. So 100 minus 84, 16. So 16% of 1,000 is 160. So meaning to say greater than data values which are greater than how many data values or how many stations, something like that, no? Greater than 3.28. We have 160. 160 stations charged greater than 3.28 for a gallon of regular gas. No? That's additional problem. No? Additional problem. To distinguish less than to more than. Okay? So now let's go to the next problem. Which is, this one is like continued. No? Again, the one I mentioned. No? More than. No? More than 3.46. So where's the 3.46? This one, right? This is the 3.46. But we know this is two what? Two standard deviations. And we know the percent here, if you consider that u plus 2 standard deviation and the mu minus standard deviation, we answered that already. That's 95%, right? So meaning there's a 5%. Where's the 5%? It's divided into two. The 2.5 here, the other 2.5 here. Since we want greater than 3.46, just get the 2.5%. So 2.5% of 1,000 is 25. So the answer to that problem is 25 stations. Okay, this problem. 25 stations charge more than 3.46 for a gallon of regular gas. Did you get the how to solve it? Again, the 3.46 and the 2.74 is what? The two standard deviations, no? Above and below the mean. And that represents 95%, right? According to the empirical rule. So there's another 5%. Where's the other 5%? It's divided into two. The 2.5 on the left, the 2.5 on the other left. And since we want to know how many stations charge greater than 3.46, so you just get 2.5%. But if you want to know how many stations charge less than 2.74, that's another problem. Then also the same, no? 2.5 times 1,000. So 25 also. 25. But the problem is about this, no? More than, no? But I just added this, no? What if I want to know the number of stations which charge less than 2.74? So same answer because 2.5, 2.5. How come I divide into 2? Because symmetric, remember? The property of symmetry. Okay? So that's how you answer this, these problems, no? Using the empirical rule. Okay, class? So what's mentioned here, explained already, no? What mentioned here, the one I explained, no? That's why we divide this 5% into 2, no? Because of symmetry. So in effect, we only want the 2.5%. Okay? So I think the next one is the third part, if I'm not mistaken. Okay, wait. Let me just remove the pen. It's also, yes, the standard normal distribution. The standard normal distribution class is still normal distribution, but there's a property of this. That's why it's called standard, no? that's only applicable to the standard normal distribution. It's like function and relation. No? A function is a relation, but there is this property of a function which can only be found in this function, no? Not in other relation. No? Same thing with the standard normal distribution. There's a property here that can be found in standard normal distribution, but you cannot find in other normal distribution. And what is that property? Okay, let's dive in. So, and how to get this, no? Standard. So, standardized, no? From a normal distribution, you can standardize it into a standard normal distribution according to this website, no? So, meaning if you have these data values ranging, no? These data values, probably the 950 is the smallest, the highest is 1070, and then your data are graphed here, no? Are already graphed here, the data values. Okay, you have a big data ranging from 950 probably or 1070 or even less than this, no? Actually, it's not shown, no? The minimum and the maximum. So I'm just assuming, no? That's your normal distribution. We can translate it into a standard normal distribution by standardizing, no? So we can change the this one is the let me write it. So this is your mu. So your mean is equal to 1010. And then by standardizing, you can change it to 0. So how do you do that? But you're referring this 0 is the same thing as this, no? So there's like a transformation or a conversion that happened here. And what is your what's your sigma here, class? Again, this is sigma, standard deviation. What is your standard deviation here? Subtract the 2. 1030 minus 1010 is 20. So that's 20. Whereas here, class, what's your standard deviation? The standard deviation is 1 because 1 minus 0 is 1. 2 minus 1 is 1, and so on and so forth. So you notice, what is that property that I'm talking about? This one. Standard normal distribution, always the mean is 0. The standard deviation is 1. Whereas a normal distribution doesn't have to be like that, no? Like this, no? Not 0, not 20. Question is, how do you convert? How do you standardize it? How do you make it 0? How do you make it 1? Okay. It's connected to what we studied in part 1, no? The z-score. It has to do with the z-score. Okay, to come up with this. Okay, let's discuss more first. Okay, in general, yeah, in general. So I made it like this, no? This one is more specific, but I can think of this as equal to the one I discussed in normal distribution. This is mu plus 1 sigma. So this one, what's this? Mu plus, in fact, it's true, right? It follows because of the values. Now, if you use the value, it's true because 20, no? So 1010 plus 20 is 1030. So 1010 plus 2 times 20, 40, 1050, and so on and so forth. So similarly for this one can be mu minus, no? So in general, no? So it follows what we discussed, no, in normal distribution in the second part. No? It follows the labeling, no? And so on and so forth. So, and that's what we see here also, no? It is followed. Now, using this transformation, we can have this. Okay, but again, how? According to this website, no? Again, I got this from this website, no? So this one is the mu. This one is the standard deviation, no? This one possible not 0, not 0. This one possible not 1. Okay, this is the general, more general. This one is more specific. But again, since it's standard normal distribution, so it's a normal distribution. Properties of normal distribution are satisfied here because this is also normal distribution. Okay. So now let's discuss more. Okay, now from this website, it's mentioned that now using the z-transform. Yeah, this one. Remember this one in part 1, the z-score. This is, in fact, we can change this to diba? Sample mean, and then this one is the sample standard deviation. But this one referring to the population, that's why we use the population mean, population standard deviation. So using the z-transformation, so using this, any data set that is normally distributed, as long as normally distributed, can be converted to the same standard normal distribution by this conversion. Okay, when you do that, the mean will become 0 and the standard deviation will become 1. Where x is normally distributed, I will talk about random variable on the 12th week, no? Where x is the normally distributed random variable and z is a random variable. So it's also a random variable following the standard normal distribution. The only difference is that this one now is standard normal Whereas here, it's just a normal distribution. But using this transformation, we can convert it to z, the x to z. Okay, it's like xi, you convert it to c sub I. You can convert it to c sub I. When you talk of a particular score or particular data value, no, using this formula, wherein this is like x sub I. No? Okay, so we can get this. And this is like z sub I. Okay, that is why we get 0. No, we get 0 because notice that when the x is mu, then if you put here mu minus mu is 0 divided by this is 0, which explains how z transforms our mean to 0. Okay, now let's go back to this. So how did we get 0 here or here? More specific, how do we get 0? Because of that formula, z is equal to x sub I, no? X sub I minus mu divided by standard deviation. So let us say your x sub I is 1010, but this is 1010. So 1010 minus 1010 is 0 divided by 20 is 0. That's why we get 0. How about the 1? So x sub I is 1030. So 1030 minus 1010 is 20. Divided by 20 is 1. And so on and so forth, even the 2 and the 3, right? For this 1, 1050. So 1050 minus 1010, which is the mean, is 40. Divided by 20, which is the standard deviation, is 2. That's why we get 2. And so on and so forth. This one negative class because x sub I is less than mu. For example, 990 is the x sub I. 990 minus 1010 is negative 20. Divided by 20, negative 1. 970 minus 1010, negative 40. Divided by 20, negative 2. And so on and so forth. So that's how you standardize. No? Just use this. It's simple as that. Okay. So now what's the use of this standard normal distribution, you may ask? No? What's the use? How come we need this? No? How come we can just stick to this one? Okay, I'll discuss this more later. No? For now, let's tackle first the properties. No? I think it talks about properties now. Yeah, the properties of standard normal distribution. This one is already mentioned. No? It's a bell shape, symmetric about its mean because it's a normal distribution. So just like normal distribution, standard normal distribution is also bell shape and symmetric about its mean. The only difference is that for standard, as mentioned already, the mu is 0, the standard deviation is 1. But this one is also similar, not to the normal distribution. The total area, so now we're talking of area. No? A while ago, we just talked of probability. What else? Percent, decimal. But as I mentioned, as we continue our discussion on distribution, we will deal with probability, which is in the form of decimal instead of percent. And also the area. Okay? The area is associated to the probability. You notice here in the where is that? When we talk about normal distribution, this is area. Okay? So if you put it in a decimal form, so if the area here is 1, now 1, no, not percent. So the area of the green is 0.68 or 0.682. No? For the yellow and the green and the yellow here, 0.95 is the area or 0.954. And then if we add all the areas of the red, the yellow, and the green, no? 0.997. So the whole area is equal to 1. Okay. So you can think of that decimal as the area or probability. Okay. Area or probability under the curve. Okay, class? And the total area, as mentioned, is 1. No? And then this one, yeah, same as normal distribution. There is a horizontal asymptote, which is the x-axis, meaning even if you decrease the values of x indefinitely, or increase without bound, or decrease without bound, or indefinitely, excuse me, the graph will not intersect the excuse me, the x-axis. No? They will never intersect. That's the concept of asymptote class, right? That's the concept. But despite that they don't intersect, still, if you add the areas of all those still be 1, even though it doesn't end, no? Even though it will not end, if you consider the area of everything, still 1. despite that it doesn't end, no? Because you might think it doesn't end, so probably the area is greater than 1. No. So that's the mystery of that the mystery of that asymptote, no? Because if you will think of it logically, it should be greater than 1. How come still 1? Okay, so it's the mystery, not really mystery, because you can actually prove it, no? In a way. But if you will look at it without knowing the proof, it seems like wrong, no? It seems like wrong, but it's correct. It's always 1, and there's a proof for that. Okay, so we will not tackle here now. You can you probably refer to this website or research more about it. How come it's always equal to 1, despite that this one will not stop, no? And because it's very, very small, no? That's why it's closer to 0. So that's one reason. That's why if you add all of them, still equal to 1. Okay. So now to proceed. Okay, this one is mentioned just to emphasize, no? Standard normal distribution is a normal distribution with a mean 0 and standard deviation of 1, as mentioned in your module, no? And also this one is also mentioned in your module. The tables and calculators are used to determine the area under a portion of the standard normal curve. So again, area is mentioned, no? Which is associated to that decimal or to that percent that we've been talking about a while ago in the first part when we talk about frequency, no? Relative frequency distribution or frequency distribution. Actually, we're talking here of the area, no, or the probability, no? Although at that time we just talk about percent, decimal, but actually for the application we have to associate it to probability and area. So now, as I mentioned, what is the importance of standard normal distribution? Why do we need this? Why not just stick to normal distribution? Because if you notice, class, we'll be limited in solving problems, no, in the applications, because the applications is just focused on the empirical rule. Remember, if you want to know the percent, we only use the empirical rule. Only this 3%, 68%, 95%, and 99.7%. Whereas if we have the standard normal distribution, we can consider all the percents, all the numbers less than 1. And that is shown in the table that I will show to you now. That here we cannot just talk of 0.68 only, or 0.95, or 0.997. We can talk of other percents, a lot of percents, no? So that there will be more applications. Okay, let me show you the table now, where we don't only see those three. So that's here, but it's smaller, no? It's very small. So that's why I decided to divide this into 3, no? So this one, class, are decimal now, no? Decimal, which is less than 1. Less than 1. So if you want to put this in percent, put it in move the decimal point 2 places to the right, no? That's how you do it, no? 2 places to the right. Now let me divide this into 3 so that it's easier to understand. But again, when we talk of the standard normal table, usually decimals, no? Decimals less than 1 but greater than 0. So how do you understand it? Now we have the z, no? It's not the x anymore, it's the z value, z score. So entries in the table give the area under the curve, no? Between the mean 0 and the z standard deviations above the mean. For example, if you have 1.25, so that's 1.25 standard deviations above the mean, right? The area under the curve between the mean 0 and the 1.25 is this. Where did I get this? In the table. So you have to locate the 1.25 in the table. So I have here another table and another table. I divided it into 3, as I mentioned, no? So where can I get the 1.25 here, right? So 1.25, so 1.2 up to 5. Now where's the 5? So here, I think here, 0.05. So there. So you notice the intersection. So we get this, no? That's how we get it, no? 0.3944. Okay, where is that? That's how you get the 0.3944. And that's in percent, that's 39.44%. But again, usually we talk in decimal, no? In decimal. Okay? So you notice it's not anymore what? 68 or just 97, no? Or 95, no? We can have other percents. So that's the use of the standard normal distribution. That's the importance. Okay? So now we can use this now in solving other problems, no? For example, this problem, find the area of the standard normal distribution between this and z equals 0. So again, this is the same as 1.44 because of the symmetry, no? So what do I mean by that? So for example, this one is 1.25. There's a negative 1.25 here, no? With the same area because of symmetry. So what's the area here? if it's negative 1.25, also 0.3944. So the area from negative 1.25 to 1.25 is times 2. You add the two areas. Okay, because in the table, what you have is from 0 to the z. That's what it's mentioned in the table. So in the problem, you have 1.44, 0 to 1.44. So just look for the, because we don't have negative, it's the same thing as 1.44. So where is the 1.44? So again, this one, 1.4, and then 0.04, no? So you notice we have this one. So we got the answer. That's why the answer there is round off. Now you can round it off. So we get, where is that? This one, no? We get 0.425. Simple as that. That's how you answer it. Okay, so next problem is to the right of 0.82. So find this in the table, no, 0.82. Where is but you have to focus on the right, no, because there is usually what's given there is to the left. No, the area that is given there is to the left of 0.82. So where's 0.82? So 0.82, so here and then here. But this area is from to the left, 0 to 0.82. This area. But what we want is to the right of 0.82. So meaning, if you have this one, so 0.82 can be this, right? Probably here. Okay, 0.82. So the area of that, this one, okay, let me erase this to be clear. So let me, I'm sorry. But let me use a different color pen, but different color. So probably red. So let me use red. So this one class, this one. The area here from 0 to ano to 0.82 is that one that I showed to you. 0.82. This one, 0.294 if you round it off. Okay? 0.294. But what we want is the area to the right. No, the area to the right. So meaning what you want is, okay, problem with using the color. So let's use the probably the green. So what we want is the area here, no? It's to the right. But we know that the area of the, if you add the two, what's the total area? 0.5, right? Because half of this is 0.5. So if you want to get the area of the green, all you have to do is 0.5 minus 0.294. Okay, that's why we have here, that's why we got that solution. 0.5 minus 0.294 is 0.206. So meaning the area of that green one is 0.206, which is the answer to the problem. Okay, I think that's clear. Because of symmetry, this is 0.5, this is 0.5, right? So the whole thing is 1. Since this one is, so to get the area of this, 0.5 minus the area of the red, we get the area of this to the right, no? To the right of that point, what is that? 0.82. And the answer is 0.206. If you want to put it in percents, that is 20.6%. Okay, class? So I think that is clear. I'm not sure if this is the end of it. Probably it's the end of the, yeah. Oh, yeah, it is the end of it, no, class? So if you want to explore more on this topic, you can refer to this website. No? Refer to this website. Okay, so I think that's it. So that ends the lesson for this week, class. Thank you very much for attending.